Alright, for section 6.4, we're going to look at solving equations containing rational expressions. So if you remember, the last thing that we looked at in the last lesson was looking at a rational function. And you know, anytime we talk about a function, we have to think about domain. When we looked at polynomial functions before from test 1, you remember we had things like f of x equals negative 2x squared plus 3x plus 1. And we talked about stuff like what would f of 1 be. When we had polynomial functions, the domain was all real numbers. And that's because the definition that we had of a polynomial, the only things that can happen is we might be raising a number to a power, or we might be combining them by adding, subtracting, multiplying, or dividing. But when we think about a rational function, we have to be more careful about the domain, because now we're going to have one polynomial divided by another. So we're going to have a variable in the denominator. So anytime a function has a fraction where there is a denominator, especially if there is a variable in the denominator, we have to make sure we don't end up dividing by 0. So the domain of a rational function is the set of all possible x values at which the rational function can be evaluated. And the only real value or values that we have to be concerned with is an x value that would make the denominator equal to 0. So when we solve rational equations in just a little bit, we're going to need to determine the domain so that we'll know if any of our possible solutions need to be rejected because they're not in the domain. Alright, so first we're going to start looking at how to determine the domain of just a rational expression. So we don't have any equals in these. So remember we said that the domain with rationals, that the issue is that the denominator cannot be 0. So we can find the domain of a rational expression by setting whatever the denominator is equal to 0 and solving for the variable. So in problem number 1, we don't have to concern ourselves with the numerator at all. We're only worried about the denominator. So I'm going to take the x minus 5 and I'm going to set it equal to 0, which is the one value that it's not allowed to be. And we're going to solve this for the variable. So this is x to the first. That's just linear. So all we have to do to solve this is add 5 to both sides, and I get x equal to 5. So what we have just found is what you can think of as our bad value. This is the number that we cannot use for x in this rational expression because it makes the denominator 0. So for the domain, we're going to say that x cannot be equal to 5. So notice the not equal to. That's very important. If you leave it as x equals to 5, then what you're telling me is that 5 is the only value that's in the denominator, instead of the right answer, that 5 is the only value that it cannot be. All right? So for the second one, again, we're only interested in the denominator. So I'm going to take x squared minus 3x minus 10 and set it equal to 0, the one value that it's not allowed to be. This time, my equation is quadratic. We have an x to the second. So the only way that we've learned to solve these so far is by factoring and using the zero factor property. So since I have a equal to 1, I know that I need an x in both of my factors. And then my c is negative 10 and my b is negative 3. So I need factors that will multiply to negative 10 and add to negative 3, just like we've been doing all along. So that's going to be minus 5 and plus 2. And this should look familiar now. Now I have two factors set equal to 0. So we can solve using the zero factor property. So we let x minus 5 equal to 0 and x plus 2 equal to 0, and we solve each one. So if I add 5 to both sides, I get x equal to 5, and if I subtract 2 from both sides, I get x equals negative 2. And remember, these are my bad values. So the domain is x cannot be equal to negative 2 or 5. All right, let's look at one more of these. And this one looks pretty complicated, right? It looks like maybe it's a little intimidating to start with. But remember, we don't care what's in the numerator at all. So we're going to start just like the others. I'm going to set the denominator equal to 0. And the first thing I see, not only do I have 4 terms, but all of the terms on the left-hand side have at least an x to the first. So I'm going to start by factoring a GCF of x. So that will leave me with x cubed plus x squared minus 4x minus 4 equals to 0. Now the remaining 4 terms, there is no other GCF other than 1. So now I'm going to pair them off. My first pair has a GCF of x squared, and that will leave me with x plus 1. My second pair has a GCF of negative 4. That will leave me with x plus 1. And then if I factor out the common binomial term, and what's left is the x squared minus 4, I get here. Now this problem is probably close to a worst case scenario that we would ever see or deal with. If you notice, this one is still a difference of squares. So even after all that work, we have one more step just to get it factored. X squared minus 4 is a difference of squares. So we can write that as x minus 2x plus 2. And now we use the zero factor property. We'd have to set each one of those 4 factors equal to 0. So we'll let x equal to 0, x plus 1 equal to 0, x minus 2 equal to 0, and x plus 2 equal to 0. So x equals 0, we're done with that one. Then we would need to subtract 1 to get x is negative 1, and then add 2 to get x equals 2, and then subtract 2 to get x equals negative 2. So this problem has 4 bad values. So for the domain, x cannot be, and it doesn't matter what order you write these things in. I'm going to write them from smallest to largest, but it really doesn't matter. So I'm going to say x can't be negative 2, negative 1, 0, or 2.